Today we're going to be looking at factoring special products. All right, so start with your state standards and your success criteria. So to be successful today, you need to be able to factor the difference of two squares, factor perfect square trinomials, solve real-life problems by factoring using special product patterns. All right, so you may remember this from a couple sections back when we were multiplying using distributive property and FOIL. We looked at these a little bit going from the other direction. Now we're going to look at them as a difference of two squares. So if you have a squared minus b squared, that equals a plus b times a minus b. So same binomial, different sign in the middle, is always going to be a difference of squares. That should be easy to recognize when you see a problem that has a difference of squares. It should be easy to recognize because it's two perfect squares, and then you can go straight to factoring. Again, this is a big topic on the ACT. Learning these special patterns is really helpful on a timed test like the ACT. All right, the second thing, the key idea, perfect square trinomial pattern. So we have a squared plus 2ab plus b squared equals a plus b quantity squared. If you remember when we were multiplying before, we started with the a plus b quantity squared. We multiplied it out to get this. Now we're going to start with this and we're going to factor it. So again, we're just going kind of in reverse of what we did a few days ago. All right, in understanding perfect squares, it's helpful to remember what is a perfect square. A perfect square is a number times itself. So if you review this multiplication table is here, all right, if you learned your multiplication, which you should have in about the third grade, then you would know these. If you recognize these numbers down the diagonal, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. Those are all your perfect squares. That's the time when the number is multiplied by itself. For instance, 4 times 4 is 16. 5 times 5 is 25. So this is handy to review and remember. Those numbers down the diagonal are your perfect squares, and you should recognize those when you see those as perfect squares. All right, example 1, factoring the difference of two squares. Again, if you have a difference of two squares, then you have two binomials. The only difference is the sign in the middle. So two binomials, same binomial, different sign in the middle. So we have a perfect square. We have another perfect square. 25 is 5 squared. So x times x, 5 times 5, we have a difference of squares. We can go straight to this difference of squares pattern. So I know I'm going to have x plus 5 and x minus 5. Now the order in which you write the sign does not matter. If you wrote x minus 5 times x plus 5, that's the same thing. So it works very well regardless of which way you write it. And it does have to be a difference just to indicate this cannot be a plus. It doesn't work if you have a plus there. So it does have to be a difference of two squares. All right, so B part. We've got 4z squared. 4 and z squared are both perfect squares, and 1 is a perfect square. 1 times 1 is 1, so that is a perfect square. So we're going to have 2z plus 1 and 2z minus 1. All right, and C part, 100 is 10 times 10. M squared is m times m, so we have a difference of squares here. So we're going to have 10 plus m and 10 minus m for our difference of squares there. Once again, you can always multiply to make sure it works out. So 10 times 10 is 100. Minus 10m plus 10m, cancel the middle term. M times negative m is negative m squared. All right, example 2, evaluating numerical expressions. All right, so it says use a special product pattern to evaluate the expression. Sometimes when you have larger numbers, you can find the answer quicker by using a difference of squares pattern. So anything squared is a perfect square. So I've got 54 squared minus 48 squared. So this is a difference of squares. So I can rewrite this as 54 plus 48 and 54 minus 48. When you do that, it becomes a little bit easier to calculate in your head. So if you do 54 plus 48, that's going to be 102. Hopefully you can do mental math to add those together. And then 54 minus 48 is 6. So 102 times 6 is 612. So I could do that without a calculator using the difference of two squares pattern. Again, 36 squared minus 34 squared. I can use a difference of squares pattern. I can do 36 plus 34 and 36 minus 34. All right, so I know 3 and 3 make 6, 6 and 4 make 10, so that's going to be 70. And 36 minus 34 is 2. And then 7 times 2 is 14, so just add the 0, 140. So again, this helps you calculate large numbers a little bit easier. The main thing is recognizing that you have a difference of two squares so that you can write it in this pattern and calculate it quickly. All right, moving on to example 3, factoring perfect squared trinomials. All right, so this one is n squared plus 8n plus 16. So we're talking about perfect squared trinomial patterns now, and it's a squared plus 2ab plus b squared. And we can go straight to factored form as a plus b quantity squared. So how do I know if I have this pattern here, if it shows up like this? Well, 1 squared or n squared. 1 and n squared is both perfect squares, so a would just be n. And what number squared is 16? 4. 4 squared is 16. So 1 times 4 is 4. And then twice 4 is 8. So you can see the middle term has got to be twice AB. So if you can determine what A and B are, you can quickly determine if this fits that pattern. Well, this one does. And so we can quickly go to n plus 4 quantity squared. Now, you can check that because n plus 4 quantity squared is the same as n plus 4 times n plus 4. And after you practice this for a while, you won't need to check it because you're going to understand that it works the same way every time. But the middle term is just kind of built in. N times n is n squared. N times 4 is 4n plus another 4n is 8n. That's where that twice, your AB, comes because it shows up twice. And then 4 times 4 is 16. So this right here is just a condensed way of writing that. And that comes from knowing the pattern here. You can go straight to factored form, which again on time tests like the ACT is phenomenal. And there's always factoring on the ACT. All right, let's look at B part. 4x squared is my first term. That represents a squared. So what would a be? A would be 2x. And then b squared is 9. So b would be 3. So 2 times 3 is 6. Double that, you get 12. So you can see that this does fit the pattern. Because it has a negative in the middle, you're going to use the a squared minus 2ab plus b squared, which turns into a minus b quantity squared. So I'm going to do 2x minus 3 quantity squared. And again, you can check that quickly if you want to. 2x minus 3 times 2x minus 3. 2x times 2x is 4x squared. 2x times negative 3 is negative 6x. I've got another negative 6x in the middle, again, hence the twice that term in the middle. And then negative 3 times negative 3 is positive 9. So you can see that that checks out as well. Very quickly, easy to factor, also easy to check. All right, C part, 9z squared plus 36z plus 36. 9z squared, if I have this is my a squared, my a would be 3z. 36 would be 6 squared. So 3z plus 6, quantity squared, or 3z plus 6 times 3z plus 6. Again, you can check it. 3z times 3z is 9z squared. 3z plus 6, or 3z times 6, I should say, 18z. 6 times 3z is another 18z. 18 and 18 give me 36z in the middle. 6 times 6 is 36. So it's always good to check your answers, especially as you get started. Make sure that you put a and b inside the parentheses, not your a squared or your b squared. All right, next we're going to look at solving a polynomial equation. All right, example 4 says solve. The first one has two fractions in it. A 3 and a 9 are the two denominators that I see. Okay, this can be factored, but it's going to be a little bit more difficult if you don't have whole numbers. You can easily multiply by the least common denominator. All right, 3 and 9 both go evenly into 9. So if you want to multiply this whole equation, both sides, left and right, by 9, and then you rewrite it, it'll make it a little easier. So I can do 9x squared. 9 times x squared is 9x squared. 9 times 2/3. 9, you can just pretend like 9 is over 1. All right, remember, you got to remember how to multiply fractions. 9 by 3 reduces. 9 divided by 3 is 3, and then you multiply the 3 by 2. So 3 times 2 is 6x in the middle, and then 9 times 1/9 is just 1. So I'm going to say plus 1. And then if I multiply 9 by 0, anything times 0 is still 0. All right, so all that does is make it look a little easier. You don't have to multiply by your least common denominator, but it does make it a little easier for a lot of you guys that prefer to work with whole numbers instead of, or integers instead of fractions. All right, now 9x squared, that's a perfect square, 3x, and then 1 times 1 is also a perfect square. So I can use my perfect square pattern now. 3x plus 1 quantity squared equals 0. So I can go straight to factored form. Remember, a times b is 3x, times 2 is 6x. So you can check that quickly to make sure your middle term works as well. And then once you get here, you can solve. You can solve this by using the zero product property. So we are going to use the zero product property that you learned a couple lessons ago. So we've got 3x plus 1 equals 0. We have that twice, so we can write it twice, even though we're going to get the same answer both times. But minus 1, 3x equals negative 1, divide by 3, x equals negative 1/3. Same thing. 3x equals negative 1. So this one has a multiple root. So it has a root of negative 1/3, and it shows up multiple times. All right, let's look at the second one. A squared plus 6a plus 9 equals 0. A squared, so I know a, and I know that 9 is a perfect square. So 3 squared is 9, so I can say 3 here. And then I can say plus a plus 3, that comes from the sign in the middle. And then I know that is squared equals 0. So I'm going to say a plus 3 equals 0. And again, you will find that you don't have to do this twice. You know you're going to get the same answer each time. But this shows that you have a multiple root. And you do want to indicate that you have a multiple root because this is a quadratic, this is a squared term, which is a quadratic expression. All right, so I have n squared minus 81. So I have a perfect square minus another perfect square. Remember, 9 squared is 81. So this is going to be a difference of squares. So n plus 9 times n